Hi, my name is Farah Shammout. I'm an assistant professor emerging scholar at NYU Abu Dhabi, and the title of my presentation is An AI System for Predicting the Deterioration of COVID-19 Patients in the Emergency Department. So before I get into the details of the project, I would first like to provide some background and context into why we are doing this. As of September 10, 2020, there are currently 28 million confirmed cases of COVID-19, including 900,000 deaths. This figure shows the number of recorded cases in New York during the first wave of the pandemic. We started working on this project in approximately the last week of March. The coronavirus has obviously impacted our lives in so many different ways, but it has specifically impacted hospitals. So imagine one patient here arriving to the emergency department with symptoms of fever, chest pain, or shortness of breath. The symptoms may become even more serious, and the patient may require hospitalization to stabilize the condition. If the patient becomes seriously ill, they might even be transferred to the ICU for intensive treatment. If the patient deteriorates even further and their lungs collapse, then this may require the insertion of a tube through the mouth and into the airway to place the patient on mechanical ventilation, a procedure often referred to as intubation. If respiratory dysfunction worsens, then this may even become a source of serious morbidity or mortality. And this is just one patient. So imagine what this would look like with the surge in the number of patients arriving to the emergency department during the pandemic. Motivated by this use case, our goal was to develop an AI system that can assess clinical decision-making in the emergency department, since it involves critical decision-making for patients in need of immediate care. So we had two main objectives. The first objective was that at the patient's arrival to the ED, we would like to predict the risk of deteriorating in the near future, defined by 4 time windows: 24, 48, 72, and 96 hours. We also wanted to predict how this risk may evolve over time. We focused on 3 main adverse events, which were ICU admission, intubation, and mortality. Now, what makes the clinical setting so unique is the availability of large amounts of clinical data that gets collected on a daily basis. So this presents a great opportunity for the use of AI and data science. For example, X-ray scanning is a commonly used procedure to assess and evaluate patients with COVID-19. Vital signs can reflect the patient's physiology, and they get very frequently collected. Lab tests can even provide more insight on the patient's status, as they reflect whether there are any infections that are present or organ dysfunction. So we decided to focus on the use of chest X-rays because they're commonly used to assess COVID-19 patients. Using a dataset collected at NYU Langone Health from 3,660 patients, and around 6,000 chest radiographs, we designed an ensemble model that can predict the risk of deterioration, provide explainability to the user, as well as compute deterioration risk curves. This was done using a gradient boosting model that learns from clinical variables and a deep learning model that learns from the chest X-ray images. So now I'd like to show some details about the deep learning model, but I won't go into depth. So on a high level, the model learns through a global module that extracts saliency maps for explainability. It also includes a greedy algorithm that extracts regions of interest with attention scores, and a local module that computes the final prediction. So this is the model that learns from the imaging data, and we also had another model that learns from clinical variables, but it was simply a gradient boosting model. So now, what are the exciting results? First, chest radiographs are commonly used for diagnosis rather than prognosis. So our results show that chest radiographs actually contain useful information for patient prognosis. They also contain complementary information to data that's commonly used for prognosis tasks, which are clinical variables, the vital signs in the labs, as I've mentioned. Overall, the combination of both modalities improves the performance in predicting deterioration across all tasks between 24 and 96 hours. We used a simple ensembling mechanism to learn from both the imaging component as well as the clinical variables component. The second exciting result is that the model offers explainability to the user. So this is an example of a patient that eventually gets intubated in 48 hours. As you can see, the model highlights areas where there are diffuse airspace opacities, which reflect that the lung has been filled with liquid instead of air. The regions of interest also highlight the most important regions within the medial right basilar and the left peripheral basilar. We also compared the performance of our system to two readers. Despite differences in years of experience, 3 and 17 years respectively, the model performs comparably to both radiologists. This highlights the potential of our model in assisting in situations where there are shortages in radiologists. Finally, as I've mentioned, we were also interested in computing deterioration risk curves that can help clinicians in prioritizing who's likely to deteriorate faster. So as you can see, the patients who deteriorate are labeled with the red line, and the patients who actually survive are labeled with the blue dashed line. So overall, our study has several implications. First, chest radiographs are useful for prognostic tasks, even though they've been commonly used for diagnosis tasks. Chest radiographs and clinical variables contain useful and complementary information, which highlights the potential of multimodal learning in AI for healthcare. Future work will investigate the generalizability of our system on different patient demographics, because our patient cohort was mainly in New York, and our data-driven tool can be really useful in pandemic hotspots where patient triage is critical. Thank you for listening, and you can find our paper on arXiv. But just to conclude on a final note, that our work truly exemplifies the benefits of multidisciplinary collaboration between data scientists, engineers, computer scientists, and health practitioners. And I'd like to thank our great team that spans across NYU Langone Health, NYU Center for Data Science, and myself at NYU Abu Dhabi.